Hello, we are solving KLA semiconductor image restoration problem. The challenge is not simply to make an image look cleaner. The input is a low resolution, degraded inspection image containing speckle noise, additive Gaussian noise, and lost spatial detail. Our task is to reconstruct the 256 by 256 image while preserving the microscopic structures that matters for inspection. The difficult part is that these structures are exactly the information that noise removal and super resolution can easily destroy. Our first question was not which neural network should we use. Our first question was what does the degradation actually look like in the KLA data? Existing restoration architectures gave us powerful features, extraction and reconstruction mechanisms. But our concern was different, whether the degradation itself changes across different spatial regions of the semiconductor image. So, before designing the architecture, we investigated the data. We first formed the residual between the degraded image and the downsampled ground truth. Across 400 matched image pairs, we analyzed 6.55 million residual pixels and compared multiple candidate distributions. The generalized Gaussian gave the strongest statistical fit with beta equal to 0.845. Since beta below 1 indicates heavier tails, this told us that the residual was not well described by a simple Gaussian assumption. But this was the only global We then divided the images into 32 by 32 patches and estimated the distribution locally. And this is where the important discovery appeared. The local beta values varied substantially from region to region. Low concrete engineering direction. We needed the restoration network to have access to information about the local degradation regime rather than relying only on the image content itself. So, the research pipeline became degraded image, followed by local distribution analysis, followed by degradation representation, followed by adaptive restoration. The patchwise analysis was our research instrument for discovering this behavior. It was not simply inserted as an offline pre-processing step into the final inference. This led to our final model, distribution mixture restoration net. The first component is the local distribution mixture head, or LDMH. Instead of assuming one fixed degradation distribution, it predicts a soft mixture over 3 learned generalized Gaussian prototypes. These degradation cues are then used through film conditioning to adapt the restoration features, and the actual reconstruction is performed by a compact NAFNet-style backbone, followed by PixelShuffle upsampling from 128 by 128 to 256 by 256. So, the model does not only ask what should this image look like, it also learns what kind of degradation is. We demonstrate the actual submitted inference pipeline. This is the same standalone inference entry point provided in our GitHub repository. The script accepts an input directory and an output directory. Automatically loads the trained checkpoint, runs the restoration model, and writes the restored images. Here we compare the degraded input, our restored output, and the ground truth. Notice the recovery of fine edges and circuit structures while avoiding excessive smoothing. This example shows the effect more clearly in a high detail region. And these examples demonstrate that the restoration is not limited to one structure. We evaluated 4 configurations under the same full-scale training protocol. The baseline achieved 28.120 dB PSNR and 0.7503 SSIM. Adding the global heavy tail formulation produces a small improvement. The LDMH model improved further, and the complete model with LDMH and film achieved our best full-scale result, that is 28.206 dB PSNR and 0. The final model contains 116,000 parameters and 4.844 GF LOPs. On our RTX 3050, it processes approximately 54.9 images per second at batch size 1. These are our local measurements, and the final competition benchmark will be performed on KLA's H100. KnowHow. Measure the degradation, understand it, and adapt the restoration.